Bismillahirrahmanirrahim. Dear student, today we are going to perform the experiment 2 of the automatic control system part of the electrical testing 3. The experiment 2 is about studying the static and dynamic characteristics of the control system. So let's start with the static characteristics, and the first experiment is we need to determine the static characteristics of the temperature control system here. Okay, so for the connections we need to refer to this diagram here. So on the board we will go to the temperature control part, and we are going to connect the y of t with the function generator, from where we are going to give the input voltage here, and the output of the sensor is going to be connected to the multimeter, which we are going to record here. Okay, so for determining the static characteristics, we need to have the input and the corresponding output, and then we are going to plot the graph to see which type of the characteristics we have for this particular control system here. So we will start by changing the value of the function generator as 2 volt, and once we change the value as 2 volt either from the board or from the software by using the function function generator tab here. Okay, so once you change the value of the voltage, once you provide the value of the voltage here, the multimeter is going to change here the output voltage, and it will keep on changing here. So we need to wait unless this becomes static, means we are going to, it stops changing here. So the final value we are going to record it. Similarly, we will change the value to 3, 4, 5, 6, and 7, and we will record the corresponding multimeter values here, and then we will be plotting it using the characteristic plotter here. So for, as you know, y of t is basically your input voltage provided using the function generator. X of t is going to be the corresponding output voltage here, which is measured using the multimeter here. So we are going to record the values here. So let's show you, like for example, if you see in the software, this is the function generator, this is the multimeter here, and we are going to change the value of the function generator here, and we are going to change to use this value here, okay, and observe this value here. Now to open the characteristic plotter, we need to click on this tab here. So when you click on this button, so the characteristic plotter is going to be opened here. For each input value, which is y of t, we are going to write the output value which we observe in the multimeter here. So now these are the final values here. For each particular input y of t, we obtain these output values x of t here. So once you fill or complete this characteristic plotter and you write the values here of the input and output, when you need to press the show button here, it is going to give you the, or it is going to plot the curve for you. Now based on this curve, we can see that for the temperature control system, the characteristic is linear or nearly linear, okay, or almost linear, you can say. It's not exactly linear here basically, okay. So this is the first part of the experiment. We also need to calculate or find the value of the kp for this particular system here. So we can calculate, so for finding the value of the kp, what we need to do here, we need to find the slope of this line here, or this curve here, okay. So since it is not a linear curve which have the constant slope throughout, what we have here basically, we can have the slope for each particular operating points here. So our operating points may be between 2 3 or 3 4 or 4 5 or 5 6 or 6 7 here. So you need to catch, or you need to move this cursor, red cursor, by holding it in the with the mouse button, and you can move it between 2 and 3, and similarly 3 and 4, 4 and 5, then 5 and 6, and 6 and 7, and the value of the gradient is going to be the slope value. So between 2 and 3, this is going to be the constant, and this is the slope here. Similarly, right now what we have the slope value of 4 and 5 here, which is 0.60 here. So we need to check for the value of the slope which is maximum among all the slope values, and it is less than or equal to 1 here. Okay, it should be less than 1 here basically, or equal to 1. So for in our case, for example, between 2 and 3, the slope was 1.07, so we will not consider this one. Similarly, between 3 and 4, the slope is basically 0.59, and the maximum slope which we got basically was between 5 and 6, which is 0.80, and this is the slope value here. This is how we measure it using the graph here. We can also calculate the slope value here. So we need to only use the simple slope formula here. How we find the slope for the point 2 and 3, 4.8 and 5.91? Simple. Just this output y2 x2 minus x1 divided by y2 minus y1. So it is going to give you the same value here. Similarly, for the next points, you can calculate between these 2 points, Assume that x is your output and y is your input here. Okay, so you can also calculate it by using the slope formula you have studied in your mathematics course here. So the next part is about studying the dynamic characteristics here. So what we have, the dynamic response of a control system, we also call it as a time response, is characterized by the transient response between the initial and final value of the output after a change in the input signal here. So what we have basically, this is for example your control system when you provide or give the input here, and in most cases we are going to give the step signal as the input signal to get the step response, or so the response of the system will be in the y of t here. So the dynamic response is basically the initial and the final value once we give the input voltage, unless it basically stop changing here. Okay, so you can see here, this is the steady state response, means the value has at the output value got stable here, so we call it steady state value, and this is still changing in order to get the steady state value here. This is the dynamic response part here. Now the experimenters the experiment is basically we need to find the Kp value and the time constant T1 value, okay, of the first order time delay element. So what we will be doing here for the first order time delay element, we will be considering a PT element here, okay. So this is the first order time delay element, and this is provided to you on the board here. So we need to connect the function generator with the input of the PT element, and the output is going to be connected to the oscilloscope in channel Y1 here. Similarly, the input which we are providing to the PT element is connected in the Y2 of the oscilloscope here. Okay. Now, next thing is we need to find the time constant by using the 63% method here. Okay. So what we have basically, this is a procedure which is already given to you in your manual here. So we are going to use the step response plotter here. Okay. So we have been provided in the software, which is just in the software of the system COM3 lab, and we can use the step response plotter to plot the step response here. Okay. So what we will be doing here, like just to first explain about the step response plotter here. So what we have basically, we have few icons here or buttons here. Okay, so when you press this button here, so this is basically going to open the step response plotter for you. So you need to provide that you need to provide the step you are changing from which value until this value. So you need to provide this one, and we need to provide the time here. So when you click from here, there is already 1 second, 2 second, 5 second, and so on. So once you finish writing these values, we will be pressing it as run here, and then it is going to take some time, maybe 1 second or more, maybe especially for 5 seconds, so 5 seconds, and it is going to plot for you the same similar type of the curve here. Okay, so now in our case, basically what we are doing here, we are changing the value of the step from 0 to 10, and we are going to run it for the 5 second duration here. So you need to give it from 0 to 10, and you need to write it 5 here, and you need to play it here. Okay, so just to show you like what we have on the step response plotter here basically. If you see here, we have a curve here basically, like for example, this is the some certain input, for example we have some output here. Now if you see here, we have different cursors here. Okay, so for example, we have three vertical cursor which is red, yellow and green. So we have the values of red, yellow and green here. Okay, of this is the time value, this will be your this signal value, and this will be the green signal value here. Okay, or input or output values here. Similarly, this is going to give you the duration between the two plotters here. Okay, or the So between red and yellow, the distance is basically in time, because we are talking about a t, is basically 3.67. So you can see, right, roughly it is like 1 point something and this is 4 point something. So this is the value here is 3.67. Similarly, between yellow and green, you have this value. Sometime what happen if your green cursor is on this side and yellow is here, so this value will be again showing you the distance, but the value will be negative here if the green cursor is on this side. Okay, so it doesn't matter, you can take the positive value. Similarly, horizontally we have two cursor, one is this green cursor and one is this red cursor here. So we can again find the distance between the two cursors, between green and yellow, between green and red here, horizontal. Okay, similarly the value, for example, right now the red cursor is here and the value is 1.3 here, for example. Similarly, this will be around maybe 0.2 value. Okay, so we can read the values here. Okay, and this is the channel, which channel we want to see here, y1 or y2. So depending upon the oscilloscope you are using, we are going to see the output waveform. If you use only y1 there in the oscilloscope, so you are going to have only one signal here. Okay, so now in our case, when we provided the value of from 0 to 10 and step values and we run it for the 5 seconds, what we had basically, we got this signal here. Okay, so we need to observe two things. We need to find the value of Kp and we need to find the value of the time constant here. So the Kp value, what we will need to do, the Kp will be equal to the output divided by the input voltages here. So simply what you will do, you can take the horizontal, any horizontal, yellow or red. Right now we have taken the red here. You can hold the horizontal red cursor and you can move it and place it on the input and the output here. Okay, so if you see here, y1 is your green signal and blue is y2. Y1 is blue and green is y2 here basically. Okay, so this is step signal is your input and this is your output here. So you can place it on the step signal, it will give you the input value, and you can place it at the steady state value of the output, which will give you the output value here. So for example, for the input value, when you put it on the green signal, the value is, since I'm using the red cursor, the value is 10.03. So this is basically the value of the step signal here, okay, or the amplitude of the step signal. For the second one, when you put it as at this point at blue, which is basically a steady state value, the value is 9.76 here. So this value divided by this one is going to be your Kp value here, which you can calculate yourself. Okay, next point is we need to find the time constant here using the 63% method here. So for the 63% method, what we need to do here, first of all, we need to go to the steady state response here. So for the 63% method, what we will be doing here, we are going to observe the output, which is this curve, blue curve, the output steady state value, which we calculated previously, which was around 9.76 here. Okay, roughly. So the 63% of this value is some value around 6.14 or something. So what we do, we need to bring the cursor to that particular point here. Maybe like you may not get exact similarly, but something close to it. For example, we got 6.17 here. Okay, so we need to place a cursor here. Now what we will do here, basically we are going to take two horizontal cursors. Now one cursor, we need to place it at the start of your input waveform, which is this step signal, and the second cursor should intersect this point here. Okay, so the distance between the two, between the red and yellow, is 1.16, which is basically the time constant, okay, of this first order PT1 element here. Okay, so this is all about our experiment here. Thank you.